presentation. Welcome to Yerba Buena Center for the Arts. My name is Katya Min, and I'm the Curator of Public Programs here. Really just very grateful that you all made it out today. Today's a very challenging, difficult day for many of us. So thank you for joining us. Wanted to also introduce Dorothy Davila, who is the Associate Director of Visual Arts at Yerba Buena Center for the Arts. She curated the Tom Sachs exhibition in our Gallery 1 and Gallery 2. Tonight's program, Life in Space from Europa to Aliens, is presented in conjunction with Tom Sachs exhibition. We are thrilled and honored to be joined by our special guests, the SETI Science luminaries, Dr. Jill Tarter, Dr. Franck Marchis, and Dr. Cynthia Phillips, for a far-reaching discussion of the possibilities for life beyond Earth. Charles Lindsay, who also helped design and pull this program together, will be moderating, and I would like to do a kind of an extensive bio introduction of him as well. Charles Lindsay is a multidisciplinary artist interested in technology, ecosystems, semiotics, and humor. He creates immersive environments, sound installations, sculptures built from salvaged aerospace and biotech equipment, videos, and photographs. Educated as an exploration geologist, Lindsay is the SETI Institute Artist in Residence Program Director, a Guggenheim Fellow, and the innovator behind OSA-Ears, project designed to deliver real-time sound data from one of the world's most biodiverse rainforests to art museums worldwide. He's widely published and interviewed and profiled. He also has a show currently up, actually starting, from in New Museum Los Gatos, and his field station installation is at Mass MoCA through spring 2017. I'm just very appreciative of all the effort that you put in to bring this amazing program to us. So, and Charles will introduce our special guest.
Well, thanks everybody for being here. For the sake of all of you coming, but also for posterity, because we're recording this, it is a very challenging day, the day after the 2016 elections. And so it's great to gather. Clearly, we need to gather on a very large level in this country and also promote minorities, diversity, and especially women into powers of more influence, into positions of more power and influence. We have a couple great women here, and also a man that I like a lot too. Very cool, Franck Marchis. So, it was a real pleasure to be invited to put together this panel. It's in conjunction with Tom Sachs' Europa show, and not surprisingly, Tom's an artist who I admire and take influence from and like very much, and it's a fantastic show. So that's really great. We're actually here to talk about the science behind Europa and beyond. And I think it's very interesting also speaking to this period we're in, where this is a great contemporary art museum, and I'm an artist, and I'm introducing three top-shelf scientists to talk largely about science. I mean, this is a science talk tonight. So that's sort of, I suppose, it's really a hybrid gathering tonight, but this territory where science not only influences the arts, but is integral to it, and vice versa, is something that's being explored at the SETI Institute in this Artist in Residence program that we have. I was the first artist there, sort of a beta test, and I worked with Dr. Lawrence Doyle. Some of you know this story he wrote, the algorithms that determined humpback whale communications exhibit syntax, so inferring its language. So that program's now gone on to have quite a number of artists. There are about 12 now. Our first wave are about to become alumni, and they are in a group show at the New Museum Los Gatos, which is also a new relationship for us, and that show's up now, so if you care to, please go. It's up till March, just opened this past week. And so we'll get on with the science here. As I said, we're going to sort of move off Earth towards Europa, way out beyond Europa, and then we're going to talk about possibilities for life elsewhere. And if they're sort of smirking watching us at the moment. We don't really know that. The scientists here, as quite a number at the Institute, have become good friends, but I'm actually going to read the bios because you know how it is with our friends. We sort of get beyond that. Dr. Cynthia Phillips is a Europa Project Science Communications Lead and Scientific Application Software Engineer at JPL, NASA's JPL. So she came up from the LA area for this, and she's going to talk about Europa for Real, which is this place that Tom Sachs has already been to and come back from, but she's going to talk about that. Dr. Franck Marchis, Exoplanet Research Group Chair and Senior Astronomer at the Carl Sagan Center for the Study of Life in the Universe at the SETI Institute. And then Dr. Jill Tarter, and this program, the SETI Artist in Residence program, came about through a serendipitous meeting between myself and Jill in New York. I'm not going to go into it. It's a fairly well-known story, but a very pivotal moment in our lives as we've become really close friends. And it's gone on to spur this program. Scott Kildall is here, one of our artists. He's San Francisco based. So that's been a real pleasure to bring all these people together. So Jill holds the Bernard M. Oliver Chair for SETI Research at the SETI Institute in Mountain View. She serves as a member of the Board of Trustees. Tarter received her Bachelor of Engineering Physics degree with distinction from Cornell University and her master's degree and PhD in astronomy from the University of California, Berkeley. She has spent the majority of her professional career attempting to answer the age-old human question, are we alone, by searching for evidence of technological civilizations beyond Earth. She served as project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observatories worldwide. She is a fellow of the AAAS, the California Academy of Sciences, and the Explorers Club. And she was named one of the top 100 most influential people in the world in 2004, and one of the Time 25 in space in 2012. She received the TED Prize in 2009, and has received 2 public service awards from NASA, multiple awards for communicating science to the public, and has been honored as a woman in technology. We actually met at Wings World Quest Awards ceremony in New York, which honors women explorers. That's where we met. In 2015, she became president of the California Academy of Sciences. Asteroid 74824 Tarter, 1999 TJ16 has been named in her honor. Since the termination of funding for NASA's SETI program in 1993, she has served in the leadership role to design and build the Allen Telescope Array and to secure private funding to continue the exploratory science of SETI. Many people are familiar with her work as portrayed by Jodie Foster in the movie Contact. And before we move on, let me just say that when we met, Jill invited me to the observatory. I took some good California red wines and went up there, and we were walking around under the dishes at night, drinking nice wine, very existential conversation, and that really birthed this program. So all of that sort of cycled into, tonight and a lot more. So really fantastic scientists and fantastic individuals tonight. So Cynthia, will you please lead speaking about Europa, and I will shuffle through some photos as you make nods or as I feel like it.
Great.
Thanks.
So again, thank you everyone for coming tonight. And for those of you who've had a chance to see the terrific exhibit downstairs, you know that it focuses on an artist's conception of a human mission, a human exploration mission to Jupiter's moon Europa. And so I'll tell you guys a little bit tonight about what we know about Europa for real, the real Europa, rather than the artist's concept of Europa, and what our plans are for future exploration of Europa. So Europa is a small moon of Jupiter. It's about the same size as Earth's moon. But as you can see in the picture above me, it looks very different from our moon. Earth's moon is covered with these round impact craters that are these old scars on the surface. And so from looking at those craters, from studying the age of the moon, we can say that the moon is an old, battered body where very little interesting geologic activity has happened over the last couple billion years. When we look at Europa by comparison, we see that its surface is very bright. We know that brightness, those white patches, that's actually water ice. And we knew that before we ever went there with a spacecraft. We could actually measure that with Earth-based telescopes. We could measure the composition of Europa's surface. So we know the surface is covered with a layer of ice, of frozen water ice. But if you look at the picture, you see that there's all these disrupted places. There's these long linear features that go across the surface. And then there's these kind of fuzzy looking regions as well. This picture uses data taken by the Galileo spacecraft. And so the colors on here are an approximation of the true colors, but the colors have been stretched and enhanced so that you can really see the compositional, the color differences on the surface. If you were just looking at Europa, it would really look very bright. It's one of actually the brightest objects in our solar system. And the patches that you see as these blues and reds in the image, they would look much paler. There would be much less contrast between those and the white background material. But when folks like me, one of my specialties is in planetary image processing. So when we put together an image, actually, can you go back? Sorry, I wasn't done with that one. So when we put together an image like this one, we try to bring out as many details as possible, as well as making an image that we feel is very artistic and sort of aesthetically pleasing. And so there really is an artistic side as well as a scientific side in making an image like this. And I have some stickers somewhere, so everyone who comes gets a Europa sticker with this picture on it when you leave. So when you look at Europa, the long linear features on its surface, those are cracks. And so those are places where the ice surface has actually cracked apart, and in some places you can see where it's moved, where they're faults, like the faults that we have here on Earth. On Earth we have earthquakes. On Europa, perhaps we have Europa quakes. That's where the edges of the faults actually move past each other, and you can see that features have moved from one side of one of these cracks to the other side. So we know that there's been motion. And so if you go to the next one, you can see here we're zooming in on the surface. And so not only are there places where the surface has cracked, where there's these long linear cracks on the surface, but in addition, there's places that look like icebergs. So we know from data taken by the Galileo spacecraft that traveled to Jupiter, it was there from the late 1990s to the early 2000s. That's the last visit that we've had that's taken close-up pictures of Europa. So all of the pictures that you see on NASA websites, on calendars, et cetera, those were all taken by the Galileo spacecraft. And we haven't been back since. But we've learned just a wealth of information about Europa's surface. And so in this picture behind me, you can see that not only are there some cracks, if you look down in the bottom corners, you can see these kind of linear features. So these are some of these cracks, these ridges on the surface. And then there's also things that look like icebergs, where the surface has actually broken up, it's rotated, it's translated. In some places, the blocks have kind of dipped down like icebergs, and then they've refrozen back into their new positions on the surface. So this is all interesting from a geology point of view, but why do we care about it in terms of life? It's because one of the things that the Galileo mission told us was that there is a layer at the surface of Europa. So again, remember, Europa is about the size of Earth's moon. But at the surface of Europa, there's a layer that's about 100 kilometers thick that has the density of water. So that's really exciting. One of the problems, though, is that the Galileo spacecraft's gravity measurements weren't good enough to tell how much of that was frozen solid ice and how much was liquid water. So it's possible from those measurements that you could have had a complete solid layer of ice at the surface, or that you could have had a thin ice layer and under that a big ocean. And so the geologists looked at pictures like this one back here and they said, well, we see icebergs. There's got to be water. We see all these cracks. We see these faults. We see motion on the surface. And the people who study composition, the spectroscopists, said, well, we see salty places on the surface where something like salt water could have come up from an ocean onto the surface. So we had all of these sort of indirect lines of evidence for an ocean. And it's this great story with the Galileo mission that basically so people with a geology background like I do, we look at Europa and we want pictures. And pictures take a lot of downlink to send back. especially with the Galileo spacecraft, which had a crippled high-gain antenna. So that meant that it was not able to send back nearly as many pictures as we'd hoped for. It was really a triumph of the mission that we were able to do as much as we could, but pictures were very valuable. They were very valuable real estate. So of course the geologists like me wanted as many pictures as we could get. Then there are also these people who did this really, what we thought was really boring stuff, these like fields and particles people who are measuring magnetic fields and all this stuff that we thought was just useless for Europa. So it turns out that these magnetic field people, they actually found a signal from Europa that was evidence of an induced magnetic field. So what that means is that you have a liquid layer you have some kind of conductor. Europa doesn't have its own magnetic field, but Jupiter has this really, really strong magnetic field. So as Europa, if you've ever taken like a high school physics class, if Europa is a conductor and it's moving through this magnetic field, you get an induced field. And so you can use physics to figure out what direction that induced field should have. And it turns out that it was exactly consistent with the presence of a large conducting layer just below Europa's surface. And it turns out that salt water, kind of about as salty as Earth's oceans, is a perfect solution to this. So, here were all the geologists were like, oh, we have these icebergs, we have this great evidence, we can't prove it, we really think there's an ocean. And then suddenly the magnetic field people were over here saying, well, we have this wiggly line in our plot. It looks really boring, we think. But the magnetic field people were like, that proves there's water, that proves there's this ocean. So it was really this triumph and this sort of this life lesson for me that you really need all these different types of data, that just because my bias is in looking at these beautiful and amazing pretty pictures on the surface, that doesn't tell the whole story. And so what we found out from the Galileo mission, though, is that yes, we have this ocean under Europa's surface. We think that it has about twice as much water as all of Earth's oceans combined. So that's a lot of water. And where we found water on the Earth, we found life. Water is really one of the essential requirements for life as we know it. And so people had been excited about the possibility for life on Europa since before the first mission got there, the Voyager mission in the late 1970s. But this new discovery of an ocean under Europa's surface really just raised the profile of Europa, and it really started setting the stage for a new mission there. And while in the artistic version of a mission we send humans there and they land on the surface and they go and drill ice, that's not going to happen anytime soon. But what we can do is we can send a new robotic mission there. And so NASA is currently working on plans for a couple different mission ideas. One of them that's a fairly developed mission would be return to Jupiter. It would be a Jupiter orbiter, but with multiple close flybys of Europa to take high-resolution pictures. And so the picture that's up on the screen behind me is our only close-up view of Europa's surface. So what you see from this, and this is a very oblique view, what that means is it's kind of like looking out the window of an airplane onto the surface. So it's very sort of like a slanted view, but you're seeing some of the topography. You can actually see that there are some of these ridges on the surface. There's these bright and dark variations that are due to the composition. You can see how lumpy, how kind of like soft and lumpy the surface looks. And so, but this is the only place that we have an image that's good. This one tiny, tiny region, less than a fraction of a percent of Europa's surface. So we need to go back. And so this new mission that NASA is planning would go back. It would map the surface at this resolution over a much larger fraction of the surface. And it would also have a couple other instruments, including a radar instrument. The radar would actually be able to detect the ocean directly. So you send a signal from the spacecraft down onto the surface. It penetrates through the ice layer into the ocean layer. And then depending on how thick that ocean layer is and how broken up the ice layer is, you could most likely be able to figure out how exactly detect how thick that surface ice layer is, and maybe even go all the way down to the bottom of the ocean if you get really lucky. So that would be really a direct confirmation of the presence of an ocean on Europa. So we're also thinking about future missions that might land on Europa. And so when we look at a picture like this one, where would you put a lander? It's a pretty tricky looking place to land. And remember, this is the best data we're going to have. So if we're building a lander for Europa, we would have to base all of our information, all of our plans for a lander on pictures like this. And this picture, because again, this is all we have. We don't have a whole bunch of these. It's not like Mars where we have 20 spacecraft in orbit taking all these pictures and mapping down to the centimeter. This is all we have. So it's a big challenge, but it's also really exciting. And so NASA currently has plans for a lander that are in a much less developed phase, but it's a concept that they're considering right now as well. And so from an orbiting spacecraft and also from a landed spacecraft, one of the real main goals of the orbiter would be to investigate Europa's habitability. So maybe you wouldn't be able to actually find life easily from an orbiter, although there's the possibility that a microbe or maybe even a small fish could, not a fish, but something could be ejected off the surface and detected directly by an orbiting spacecraft. If you land on the surface, then that could be much more of a direct attempt to detect biosignatures, to detect signs of life on Europa's surface. And so Europa is really, I think, the most exciting place to go in our solar system to look for life. You've probably heard of Mars. It's this planet. It's kind of next to Earth. People talk about life on Mars, but when they talk about life on Mars, they're really talking about old, dead, fossilized life. We think that long ago, Mars had a climate that was warm, that was wet, that could have been a good place for life. But today, Mars is cold. There's likely no liquid water. Maybe there's something way below the surface. There's some ice, but any search for life on Mars is really a search for past life. Europa could have life now. It could have an extant biosphere. It could have organisms, probably microorganisms, but they could be living in that giant ocean. And so Europa, to me, represents the best place in our solar system to go and search for life. And it's also really given us a new idea of what kind of place could be habitable. And so as we start looking at other solar systems, we'll hear from Franck about our work on exoplanets, but just in our own solar system, if we now have not just planets like Earth, like maybe Mars, that could be habitable, but we also have moons of giant planets that turn out to have habitable environments, that really helps expand our ideas of where life could exist beyond the Earth, beyond our solar system. And I'll pass it to Franck.
That was great. Thank you. So Franck's going to go a little bit further out now.
Yeah, that's very difficult after Cynthia to be able to talk for 15 minutes. But first of all, I'm going to apologize. I have a French accent. I'm French. And I got a cold at the same time because I lost my voice last night for some reasons. So I hope you're going to be able to understand me. If you don't, just let me know, and I will repeat it with my charming French accent, and you will not understand it again.
I'm going to interpret.
We're all going to interpret.
Okay, so I'm a planetary astronomer. So what we do as planetary astronomer, we study planets, we study solar system planets, but also exoplanets. So exoplanets are planets which are in orbit around other stars. I want to start my discussion with this picture. I hope you can see it, because there is a lot of interesting elements in this picture. This was taken by this photographer called Fefo Bouvier in Uruguay, in Montevideo. And this picture shows basically everything I want to explain today in my 10 minutes monologue. It's a picture of Earth. Okay, so you can see a lake here. I think it's a lake. So liquid water. As we said, we're talking about life here, and as you already say, Cynthia, we know that if there is liquid water, there is a high chance to find life there, because our life on our own planet basically depends on liquid water. Yeah, we need liquid water, and we need a source of energy. That could be a sun, that could be a volcanic activity like on Europa, or could be any kind of exotic source of energy that we don't really know about yet. But in this case, we have a lake, so liquid water, and the blue thing you see here, it's basically the proof that in this world, Earth, you also have bacteria. Those are bioluminescent algae that we can see at specific time of the year. They process, they have a very complex chemistry where they process material from the lake and they eject waste using light. And thus this light is basically the signature of this life. And then we have some more complex type of life. We have a fisherman standing here on the left on the boat. It's a complex life because it's basically an intelligent life. someone who's using an object, a boat in this case. Okay? So this human here will also be detectable. It will change the environment. We're already doing that. We're changing Earth. If you look at Earth from far away for 400 years, you will see that slowly Earth has been changing. The composition of the atmosphere has been changing. We have an increase of carbon dioxide, for instance. You also have creation of cities and light from the cities. This can be detectable from space. So let's now talk about space. So in the top here, you have basically the star that can be seen from Montevideo. If you look at the sky in the summertime, when you have a new moon, you will be able to see 2,000 stars. But in fact, there is way more stars in our galaxy. There is billions of stars. Here, using this photography, I'm sure you already started counting them, but there is approximately 2,000 of them already on this tiny field of view. What is interesting, you have a concentration of stars, a band here, which is basically the Milky Way. Our solar system, our planet Earth, orbits around the Sun, and the Sun is located into the Milky Way. The Milky Way is a gigantic disk of stars and dust. And since we are in the Milky Way, when we look up in the sky, you will see the Milky Way as a band of high concentration stars. So the ancients, and when I'm talking about the ancient, I'm talking about people who live on this planet before 1995, had no idea that there was those stars here in the skies also had planets. I'm joking here, but it's true that we had to wait 1995 to have the full proof of existence of planets around other stars. This is a gigantic step, because if you have planets, you have a lot of worlds, and if you have worlds, you could have life there. And that's the goal of my research, is to find those worlds and to find life. And life that could be biological life or could be intelligent life, technological life, using images only. So all those stars are different. Okay, they have different mass, temperature. Some are very similar to the sun. Some are very cold. They call M-type dwarf stars. And I'm going to show you. Can you just click here? There is two circles here. One of them is Proxima Centauri. This is the red dot, the red circle here. We can barely see it. Proxima Centauri, it's a star which is located at 4.2 light years away from us. And if you follow the news, you may know that at the end of August, astronomers announced the discovery of a planet around Proxima Centauri. So why is this important? Well, we have, thanks to Kepler, it's a NASA mission, we know there is a lot of stars in a lot of planets in our galaxy. We know that each star has 2 planets in average. Okay? So that's a great discovery that's been announced like 2 years ago. But now what we want to do, to be able to do, is to find those planets which are nearby us, those exoplanets nearby us. So what this team did is basically to observe Proxima Centauri for a large period of time, 2 months, every night, using a ground-based telescope in Chile, La Silla. And what they saw is not the planet itself, it's the motion of the star due to the presence of the planet orbiting around the star. It's because this is a binary system, okay? So when the planets orbit around the star also moves. It doesn't move that much. It moves, in fact, at something like 1 to 2 meters per second. And what these people have been capable of doing using this very good instrument is to detect this motion, okay? The motion of a star moving at the same speed that the human being. And this detection indicated the presence of a planet in orbit around this star. They don't know much about this planet, because what they can only decide from this data is the mass of this planet. They found out that this planet is probably a super Earth, 1.3 1.3 times the mass of Earth, maybe more. But recent results show that it should be between 1 and 2 Earth's mass. So it could be an habitable planet because it's located at the perfect place around this star, a place called the Goldilocks zone where you could have liquid water. So that's been announced in August, and I think that's been a big announcement in our field, because people have been looking for that. It's basically for us a direction. Now we know when we look at Proxima Centauri, which is a very faint star, it's magnitude 12 if you want the details, in the sky, you know that over there is a planet like Earth, slightly bigger than Earth, and this planet may have liquid water. So what we want to be able to do is to take a picture of this planet. And that's a very complicated problem because a planet is very faint compared to the star. The star is far away from us, so the planet is very close as well. Astronomers used to say that it's basically trying to see a firefly nearby a lighthouse at 4 kilometers away. Okay? It's a very challenging problem. But we are trying to do that. Let's show the next slide. In fact, a lot of people are trying to do that. We are trying to do that at SETI Institute, but also other groups are doing this. And we want to use what we call the extremely large telescope, the giant telescope that's going to be built in the next 10 years. So this is one of the projects. It's called the TMT, the 30-meter telescope. We want to build this telescope on the top of the Mauna Kea, hopefully. Is a 30-meter telescope means that the aperture is 30 meters in size. So it's big enough to be able to capture photons coming from this faint planet. It's made of segments, okay? And each of these segments need to be accurately moved, such as the shape of the mirror is perfectly smooth. It's an extreme technological challenge. On the top of that, we want to put an instrument on this camera that will be able to collect the light coming from these planets as well. But unfortunately, between the TMT, between this telescope and Proxima Centauri or Alpha Centauri, the other stars nearby, we have what we call an atmosphere. Atmosphere are great because they help us to breathe and they help us to fly a kite. But, but unfortunately, they also blur the light. Because the atmosphere of our planet is not perfectly transparent, it's also moved. So what happens is that you have an image which is extremely blurry. And it's this blurriness make it impossible to detect these planets without being able to control what we call the wavefront. I'm not going to enter into the details, but what we are doing now is to build these tiny mirrors that move 5,000 times per second. We are capable of correcting these atmospheric turbulences. And the motion of these mirrors is basically accurate to the 3 nanometers, so it's 1,000 times smaller than the width of a hair. So we are capable of controlling the wavefront continuously, correcting the effect of the atmospheric turbulences. And the goal is that the system is called adaptive optics, if you want to know the technical term. The goal is to be able to get this image. Next one, please. All right, and I'm an astronomer, I'm sorry. Astronomy is not very excited. It's a dot orbiting on another dot. But that's what we want to do. So what you have here, it's the star Alpha Centauri A on the top, for which we basically use a system to hide the light of the star, we call a coronagraph. And what you have on circle in red here, it's a planet like Earth, a cousin of Earth, that will be orbiting in the habitable zone of Alpha Centauri. This is a simulation. This is not real yet. We are working on that. This is the goal, basically. Our goal is to be able to collect photons coming from the star, coming from a planet far away, a planet that may have liquid water. And by analyzing the color, analyzing the photons coming from this planet, we'll be capable of knowing if there is bioluminescent algae on this planet, or maybe a fisherman using a different type of propulsion. And I think that's all. Now I'm going to let you talk about intelligent life then.
All right.
That was great fun. Thank you. Jill?
So Cynthia and Franck have talked about the real game changers in this field over the past 4 decades. Exoplanets, we know they're there in abundance, and extremophiles, life forms that live on Earth in environments that we once would have said would have been totally inhospitable to life because we have a habit of defining life as ourselves. And we're finally giving microbes the respect they deserve, and we're beginning to appreciate the amazing adaptiveness of life and its ability to live just about everywhere, as long as there's a little water. And so the name of the game today is to look at all of this potentially habitable real estate out there and try and figure out whether any of it is actually inhabited. And many astrobiologists are interested in looking for biosignatures and perhaps detecting microbial life. At the SETI Institute, we are also interested in finding the mathematicians, the technological civilizations that may be out there that modify their environments in ways that we can detect over these vast distances between the stars. So that's today, but I'd like to take you back now for a moment. It's very appropriate tonight. Let's go back to 1968, when Bill Anders, Apollo 8 astronaut, was coming around the far side of the moon and took this picture of the Earth rising above the surface of the moon in the blackness of space. This is the first time we saw our world as a whole planet. This was an icon that had a lot to do with the early environmental movements, being able to see our planet as a single body. This is the point of view, this cosmic perspective, which we so desperately need to help the rest of the world and our fellow citizens in this country to adopt as we try to look to our long future and solving the challenges that don't respect national boundaries on this one world. And so from this idea of seeing the Earth in space and becoming more knowledgeable about how we got here, learning only in the 20s about the fact that these fuzzy blobs on the sky were actually other whole galaxies filled with stars, and then learning that all of those galaxies are moving away from one another at increasing speeds. This idea of our current concept of cosmology and the evolution of the universe and our intimate connection with these vast distance scales and enormous time scales. You know, it takes a cosmos to make a human, right? The iron in the hemoglobin molecules in your blood, the calcium in your bones, they were cooked up at the heart of a massive star that blew up billions and billions of years ago, and then they were recycled through the interstellar medium. All of these heavy metals, these byproducts of stellar evolution and stellar death. And they found themselves in larger and larger clouds of gas and dust, which then managed to condense under their own self-gravity and form new generations of stars and planets, and in one case, us. So this idea that we are really all part of a vast universe is an idea that I think is fundamental to finding our way forward to a long future. It's the second time I've used that term. And what do I mean by that? Well, we're a very young technology, hundreds of years, in a very old galaxy. Galaxy's 10 billion years old. And we don't know yet whether it's possible to become an old technology. There are lots of things that we can see which might put an end to our world and much of the life on this planet. What we don't know yet is whether technology, in fact, ultimately can become a stabilizing influence. So Charlie, if I can have the next slide. So I'm just trying to set a context for thinking beyond Earth. So here, this is what you and I are made out of. This is stardust. This is where we actually are what happens when a primordial collection of hydrogen and helium evolves for so long that it can begin to ask the questions about where it came from. So this is all of us. And this point of view is one which I hope we can adopt and trivialize the differences among humans that we find so divisive today. That's one of the reasons that I love working on this question of the search for extraterrestrial intelligence, because we're basically asking, is there anybody else out there who has become an old technology that we can in fact discover? So if indeed technological civilizations are the natural products of evolution on a planetary surface that leads to life, sometimes to intelligence, and some of that intelligence invents technology. If that happens quite frequently out in the cosmos, but the technologies turn themselves off, do themselves in, destroy their habitats, and are short-lived, then SETI can never succeed, because you'll never have two technological civilizations close enough to one another to be discoverable at the same time, lined up in this deep time history of the galaxy, unless technologies actually last for a long time on cosmic scales. And then it is possible that two technological civilizations can be cotemporal. They can overlap in time. And so we're trying to answer that question. Is anyone out there? And can they manage to grow old as a technology? And so if indeed someday SETI succeeds, and I'll talk a little bit about what we're trying to do in order to find that success. If we succeed, even if they haven't sent us the Encyclopedia Galactica, even if there's no message encoded with information, if it's just a cosmic dial tone, if it's just a cosmic doorbell that rings, we learn this amazing information that someone else has made it through, that technologies out there are on average long-lived. And so I think that's one of the most motivational things for us here, to figure out the answers to our problems and find a way for not only humans, but all life on this planet to have a long future. So what we're doing specifically to detect extraterrestrial intelligence is to use technology, thanks Charlie, as a proxy. So we don't know how to detect intelligence at a distance. We just don't. But if that intelligence builds technologies that radiate signals at radio or optical frequencies, or construct huge astroengineering projects, move pieces of their solar system around, or actually maybe even reposition stars with respect to one another, we could, in fact, with a lot of effort, detect that technological activity and then infer that at least at some point there were some intelligent technologists who got this all going. So you see here in this image pictures of an array of radio telescopes in Northern California at the Hack Creek Observatory. They're very close to actually Mount Lassen Volcanic National Park. These telescopes have the ability to receive radio signals over a very wide range of frequencies. Franck was mentioning the atmosphere at optical wavelengths and how it's turbulent and it blurs the images. Well, at radio frequencies, low radio frequencies, we have a lot of radio noise from electrons that are spinning around the magnetic fields that wind through our galaxy. They make a lot of noise, called synchrotron emission. And at higher radio frequencies, we have water vapor and oxygen in the atmosphere of our planet, which also produce radio signals, a lot of noise. But there is this quiet region of the spectrum, quite wide in its extent, through which, except for our own technology, which is making it louder, we have a quiet window to look at the universe. And so we would like to scan that whole region of the radio spectrum, looking for signals that appear to be engineered rather than astrophysical. And simultaneously, we'd like to use optical telescopes and look for bright flashes of light from someone's laser that also don't look astrophysical because they last for only a billionth of a second or less. And so these two types of artifacts, radio signals in the terrestrial microwave window, which the artifacts that we're looking for there are very compressed in frequency, or bright optical flashes that are compressed in time. That's what we're doing today. And our biggest challenge is not detecting those signals. We've done pretty well at building instrumentation that's fairly well optimized to that task. Our biggest challenge is discriminating against signals that are potentially being broadcast by a distant technology from the signals that we use every day, our own technologies. So we have a lot of interference in this naturally quiet window in the radio and in the optical part of the spectrum. And so we have built this telescope in Northern California. It consists of 42 of these small dishes, all hooked together with a great deal of computing power. Someday we'd like to expand this to not have 42, which is a very good number for life, the universe, and everything. We'd like to build it out to 300, 350 to have more sensitivity. But the nice thing about building a big telescope out of a lot of small telescopes is that you can use it. However many telescopes you have at a particular time, you can use those. And you build more and get more sensitive as time goes on, and you get to explore farther and farther out for the same kind of transmitter powers. And so we are in an era right now where, because of the enormous increases in computing power, we're also beginning to say, well, you know, these artifacts, sure, if we found them, we'd know they were engineered and not natural. But what about signals that are more information rich? Or maybe what about signals that are carried on the backs of gravitational waves, or perhaps embedded and encoded in neutrinos or some other exotic physics? We're trying to expand away from this simple search that we've been doing. We'll keep doing that search because it's a very good search. But as we have more capability, we reserve the right to get smarter and add new things. So we're trying to figure out how to use machine learning to look for signals in the radio that are broader band, look more like noise. We're also trying to figure out how to use infrared detection systems rather than just optical systems, because as light travels through the interstellar medium, wavelengths of optical light bounce off the dust and the gas in between the stars, and they get absorbed and scattered. As you get to longer wavelengths, like the infrared or the radio, you no longer see those small dust particles, and so your signal transmits in a much less disturbed manner, longer distances. So we're trying to open up the infrared part of the spectrum. We're trying to have dialogues with the rest of the astronomical community, looking at the universe in different ways and saying, hey, you know, if there's something anomalous, something funny, don't just hide it away and make a pretty picture. Think about that. Have you maybe stumbled on somebody's astroengineering projects? So we're excited about our capabilities at the SETI Institute to do this kind of work. As Charlie said, we've been doing this not with federal funding, but with private funding since 1993. And so we need to continue to raise the funds and the public's awareness of what we're doing, and also by getting the public involved and thinking about the search, we get them to try and expand their perspectives of who they are, where they are, how they fit into the universe, how we can work together. And so I'll just end by doing a nice quote from Caleb Scharf, who's the chairman of the astrobiology department at Columbia University. And Caleb says, on a finite world, a cosmic perspective is not a luxury, it's a necessity. So that's what I'd like to have you do tonight. Expand your perspective a little bit, help us get others involved, and maybe what we really need after Brexit and yesterday's election is to work on getting everybody's perspective expanded to take in a larger view.
Wow. Yeah, could there be a better conversation on a day like this? Wonderful. So I'm going to field questions from the audience. And because we're recording, if you could just be concise, I'll repeat your question and direct it to whoever you like, and we'll sort of go through sort of organically and see where it leads. So who might have a question? Sure.
The brown lines on Europa, is there an indication as to what material that might be? What's causing the color?
So Cynthia, the brown lines on Europa, what might they be? What's their composition?
So that's actually a great question. So we have some information from the Galileo spacecraft that says that first you can say that they have some sort of non-ice material. So we know that while most of the surface is covered with relatively pure water ice, those kind of brownish looking linear features have something that's not ice. We can go a little step further and say it looks like it's a highly hydrated salt of some kind. So some of the suggestions are magnesium sulfate or sulfuric acid. the problem is that the spectral information we have from the Galileo spacecraft is it's limited in its spectral resolutions. That means you get wiggly lines, you get these absorptions, but there's a lot of non-unique solutions that you can throw in there. What's really interesting, though, is that it looks like most of the, if you look at the composition of all those linear features all over the surface, it's very similar. And so that's actually a line of evidence that tells us that those features are somehow places where material from the subsurface, most likely material from the ocean, the liquid ocean, has been brought up to the surface. And so the fact that they all have very similar compositions tells us that they are in communication with a global subsurface ocean layer, that it's not just a localized little lake or something that would then you'd expect to have different compositions at different places on the surface. The fact that they're so uniform tells us that it's this global ocean layer, most likely. And those features are also, if we go back to Europa and land there someday, we'd want to land probably close to one of these, because that's a place where, again, where if material from the ocean is brought up to the surface, that's the kind of material you'd want to sample and study and perhaps look for signs of life in.
Great. Sure. Yes, please.
I was curious, during your talk, Cynthia, the one mosaic of the close-up, your best close-up of Europa, what was the scale of that? Like how many meters or what?
So Cynthia, what was the scale of the close-up, that grid image, the third of three?
It's the resolution's about 6 meters per pixel. So what that means is that it was made up, it's a mosaic of kind of squares, if you remember it. And so each square is, if I remember correctly, it's about a couple kilometers across. So you're still seeing a pretty zoomed out view of the surface. We're not talking about something taken by, the Mars high-rise camera that's like a spy satellite in orbit around Mars. It's not like a rover picture where you're on the surface of Mars, but it's the best view that we have of Europa's surface.
Questions? Please.
Yeah, I'm curious if any of you have any comments about portrayals of extraterrestrial technology and life in science fiction and popular culture. If that's been inspiration for any of your work, or if there's anything that's science fiction particularly gets right or wrong, plausible or implausible.
So question for any of you, is there depictions in science fiction of alien technologies or aliens that inspire you or you have commentary on or otherwise?
Yeah, the aliens that I like the best are the ones you don't see, because I think that our imagination is probably too limited to conjure up what would have co-evolved with a different planet. If you just look on our planet 500 million years ago at those soft body Ediacaran fossils, which are so bizarre and strange, and all those body plans, many of them did not make it through, were not successful. So in fact, I just was down in LA last week. When did Doctor Strange preview with the Marvel folks? And I'm livid. All the aliens are bipedal hominid kinds. They may have green or pink skin, but basically it's an actor in spandex with something funny going on with their heads. It's such a limited imagination.
Frank?
I'm just going to confess that Cynthia is a Trekkie, so I'm sure she didn't want you to know that.
I'm very proud that you know that.
Now, in my case, I read a lot of science fiction literature when I was younger. I read much less now, unfortunately, but the exploration of space, especially the solar system, really come from me reading those books and reading Mars the Red, Mars the Green, and all the political underneath it and the science underneath it. That's been very important to drive me to astronomy, because I could have done plenty of other stuff, I think. But the books, the stories, and also the achievement and the impact on the human being that is described in science fiction is one of my motivation to be an astronomer.
Yeah, and I think you'll find that, most astronomers and, many scientists as well were inspired by science fiction. And so you have kind of the artistic view of what could be that then the scientists and engineers turn into what we actually can do. I've recently, since we mentioned Star Trek, I've recently been rewatching the original Star Trek with my my 11 and 14-year-old kids, and it's really fun to see what a show 50 years ago, right? This is ancient history, and yet they got a lot right. I mean, they have these pads that they're using. They have communicators that can you can hold this little thing in your hand and it chirps, and you can talk to your ship that's up in orbit. I mean, 50 years ago that was magical, and now we all have those in our pockets. So it's really fun to look at where the technology has gone. I do agree that the general sort of view of the aliens as bipedal, human-like, with a funny nose or funny ears or green skin, you can see that as some of the limitations of both our imagination, but also what we're working with when we portray actors, when we portray science fiction on film. I think that's also why what we have in books, where your visualization is really just limited to your imagination and not what you can do with a stunt actor. A lot of times, those are the ones that give you a much better view. I do have to mention that one of my favorite aliens, though, is the Horta in Star Trek. So this is a creature, for those of you who haven't seen this in a while, the devil in the dark, right? So this is a creature where these miners are dying, and there's this creature down in these caves, but they can't detect any life. There's no signs of life. None of their technology can detect it. And finally, they physically see this creature. Spock, of course, manages to mind meld with it, which proves that it's intelligent. And it turns out it's a silicon-based life form. And so that's why all of their life detectors were looking for carbon-based life. And for me, and it's this, it's not humanoid at all. It's this big kind of, thing that looks like a rocky bug or something like that. But it's intelligent, and it's just trying to protect its eggs that these miners have been smashing open, thinking that they were just rocks. So it's, it's a really great object lesson, I think, in life as we don't know it, and the fact that when we went to Mars, when the Viking lander landed on Mars to look for life, it was this huge experiment, this huge sort of technological revolution in trying to find life on another world that was ultimately controversial, but I think most people will agree it was unsuccessful. But that attempt to detect life, it was based on our view of life as we know it. It was based on certain metabolic and fundamental chemical processes. And so now, like Jill mentioned, we're seeing that life can survive and thrive on Earth in extreme environments, in ways using metabolic processes that are very different from what we humans use. So I agree. I think that we need better depictions. We need of aliens, of alien technology, and also just of the physical structure of aliens in science fiction and in our literature, so that can inspire the next generation.
So I have a question, sci-fi, but you guys go first. Yes.
I have a question for Jill. You mentioned that you're looking for new ways of finding signals and innovative, like it could be on gravitational waves. And I was wondering if we're doing anything to send signals out in these new ways.
So Jill, the question for you is basically, are we sending signals out in an effort to communicate, and your thoughts on that?
Right. We are not deliberately trying to transmit. On the other hand, we're leaking all the time, right? And since the first radio commercial transmissions, there's a sphere that's probably about 80 light years in radius that surrounds the Earth, the radio sphere. We've been generating signals that announce our presence at a low level, right? So if you're an engineer and your job is to build a television transmitter, a radio transmitter, or an airport radar, you don't put any more power into that instrument than is needed to do the job. Good engineering principle. So since you're trying to illuminate the next county rather than the next star, they're not very strong, but a sufficiently advanced technology could perhaps detect this leakage. in terms of deliberately broadcasting and putting a lot of power into signals. We haven't done that for a number of reasons. One, it's harder to transmit than receive and more expensive. Number two, if you're going to do it, you have to sign up to a 1,000-year plan, a 10,000-year plan, because it doesn't make any sense to put all this effort in transmitting a strong signal in a particular direction or in many directions and only turn it on for a week or a year or 2 years, because that signal's going to go right past your intended target, and they would have to be looking at you at exactly the right moment, exactly the right time slot. So if you're going to transmit and you're serious about that being important, you have to sign up for a long-term effort. And we're just not grown up enough yet to do that. And lastly, there's this little vexing problem about who would speak for Earth and what should they say. And that's a perfect opportunity for a global conversation. We've had a number of meetings over the last few decades. People sitting in the room are usually white, male, and very European. We've missed a lot of traditions and cultures. We haven't had a way to get them to the table. Yet, this is a question for all of the planet. Everybody should have a say in this. And so we're trying to find a technology that will allow for a reasonable conversation that doesn't get spammed, doesn't get taken over by the loudest voice or the pornographers or whatever. So it's a good problem to be discussing, and it's one that we are looking at. There's something called it's either liquid feedback or liquid freedom. It's an application coming out of Germany that says that it can be this absolute democratic conversation platform. Taking a look at that. There's also, you may remember that the Voyager 10 and 11 spacecraft had these golden records on the sides with the sights and sounds of Earth encoded in that record. And those sights and sounds were put together by a very small team of people, very exceptional people. Carl Sagan, Frank Drake, Ann Druyan, I'm forgetting. John Lomberg, and one more. He lives in Marin. He used to write for Rolling Stone. Anyway, one other gentleman. And perhaps that wasn't the best view of Earth. There have been, if you go on the website, you'll find some artists that have tried to redo the sights and sounds of Earth, and some of them are a lot darker than the very optimistic Voyager. But the spacecraft that just flew by Pluto, called New Horizons, is going on to fly by another an asteroid. And when it finishes that job and downloads all of the images, it will be done, but it is still, just like the Voyagers, going to leave the solar system eventually. And when it has downloaded all the scientific information in its memories, it is still within the reach of large radio transmitters. So we're talking about a project called One Earth Message, where we're going to try and have a crowdsourced global depiction, sights and sounds, or whatever else the world thinks best represents not only humanity, but life in general on the planet. And that's going to be coming up in the next few years. NASA hasn't given final permission to do this. The technologies of how you encode it in the memory and then make it obvious that there's there's information here to somebody who might eventually find the spacecraft. How you keep that message pristine and refreshed after you no longer have power on board the spacecraft. All interesting challenges, but I think we're going to do this. And of course, it's this idea of creating a selfie of Earth is the most important for Earthlings, right? We need to have an opportunity to say what we think about who we are and what's important.
Sir.
So earlier this year, there were reports that we may have detected a Dyson sphere. Is there any updates on that?
So the question for all of you is, there was a report of a Dyson sphere, thoughts or reports on that, updates? Frank?
So-
Jill? Frank?
Yeah.
Sure, go ahead.
So that's the Tabby star we're talking about, most likely. This is a star that has been observed using the Kepler data. So Kepler is a spacecraft which has been staring the same area of the sky for 4 years. And the goal of Kepler is to basically detect a small attenuation of the light of the star, which could be due to the transit of a planet in orbit around the star. So Kepler is capable of seeing the shadow of a planet, not the planet itself, but only the shadow. A group of citizen scientists went through the data of Kepler and found out that a star has this very weird variation of light. The variability was random, was very deep sometimes, up to 10%.
15%.
15? Okay, astronomers. 10, 15%. And I forgot the name, Tabby.
Tabby.
Yeah, but Tabby is
Boyajian.
Again?
Boyajian.
Boyajian. So it's Tabby. Boyajian is she's a person.
KI68462852.
Exactly. Thank you. I was like, when is it going to come? This star, the Tabby star, let's call it like this, we don't know exactly what is this attenuation of light is due. Tabby had plenty of explanations, and one of them was that a swarm of comets around it, but we don't know. The reason for which we don't know is because we have a few data points coming from Kepler in one wavelength, one color. Recently, a group analyzed the star, the variation of light of the star over a century using very old data taken since 1906, something like that.
More than 100 years, yeah.
And they show that the star was dimming regularly over the year. We don't know what's the source of that. Frankly, it's a mystery. It's a great mystery. The logical explanation for me is that it's most likely something natural, something we didn't yet anticipate in the formation of stars or in the evolution of stars. We are going to find out by observing this star using more instruments at different wavelengths, most likely. But it's an interesting problem. So the Tabby, you can go explain what the Dyson sphere here is.
Well,
more
the
detailed
idea,
than mine.
the problem is to block 15% of the light from the star and not do it periodically, have it happen at, aperiodically. It's really hard to come up with a model of how you get enough material between the star and the telescope to block that much light and not have any infrared excess, not to... they've really scratching their heads, and eventually someone said, well, maybe it's a megastructure. Maybe it's this huge engineering project to orbit collectors, solar collectors or stellar collectors, to harness the power from the star for the civilization that's on the planet. And so if that means potentially an extraterrestrial technology, and so we used this telescope here for about a week last October, looking at all the frequencies that we could observe, and we found no indication of coherent radio emissions. Now, the Berkeley SETI Center for Research just last week started using a telescope that has more collecting area, the Green Bank telescope in West Virginia. They're going to be looking for a while. Tabby herself has gotten time on, because Kepler can't observe this anymore. Tabby has gotten time on Las Cumbres, a collection of smaller telescopes around the planet where she can get daily cadence on this star, looking for an event to happen again. And then while it's happening, if they can come up with it, we can look at it with all kinds of other telescopes and try and figure out what's going on. As you said, it's a puzzle. It's a really interesting puzzle. So far, no reason to blame the aliens yet.
So that's why SETI is important, because SETI is also a motivation for astronomy. I mean, if the citizen scientists did not have looked through the data, informed Tabby about it, we will have missed this. Now there is people doing follow-up with SETI, and there is also follow-up using light curve observation. So we don't know if it's an alien or if it's there is a natural explanation. We're working together, the astronomy and SETI, to find a response to that. And I think that's a good way to collaborate. And most likely, my guess is going to be physical, stellar physics that we have no idea yet about. We will see. 2 more years.
So unless any of you have closing statements, maybe the scientists are going to stay. Anything? How are we? Good? So listen, I want to just...
There's one more question.
Oh, I'm sorry. Yeah, go ahead.
Well, it's really not a question, but besides this evocative and inspirational forum tonight, we have another celebratory, we have a celebratory thing to acknowledge, and that's Carl Sagan's birthday is today.
Oh,
right.
wow.
November 9th.
Thank you. That's excellent. Thanks very much for that, Carl Sagan's birthday. So I'm going to thank Yerba Buena Center for the Arts for hosting it, and thank all of you for coming at this really weird time. And thanks Cynthia, Franck, and Jill. And the SETI Institute's been amazing. Obviously, it is an inspirational thing in and of itself. There's a lot of developments there, so I would say, continue to watch the website if you care to. We have the first group show from our Artist in Residence program at the new Museum Los Gatos. Please check it out. The website's going to be rebuilt soon. And also the SETI Institute hosts a colloquia every Tuesday, almost every week of the year. So if you're interested, please come out. I think we'll break. The scientists will be here for a little bit. But thanks, everybody, for coming out. Really appreciate it. Thank you.